Hello everyone, welcome back to the latest lecture session. Very quick recap of what we discussed in the last session. I believe we were looking at different units, molar, mass per volume and so on and so forth. And also we looked at units in terms of equivalents, right? Equivalents in terms of typically H plus or charge or electrons, let's say, right? And then we looked at the conversions and so on and so forth. Let's move on to the major aspect that's going to be relevant throughout this course. Let's say I have some pictures out here. Let's just look at it first before we move on to the relevant session. Here I have, what do we say, for lack of a better term, a chimney that's releasing some particles into the atmosphere. And let's say this is the plume section, let's say, right? And let's say we have Haridwar. Assume that this chimney is in Haridwar and Roorkee is out here, and I want to know what are the adverse effects at Roorkee due to the plume or the pollutants being given out at Haridwar, right? How do I go about that? Or let us say, rather than leaving it to be pretty generic, let me be a bit more precise. I want to predict the concentration of pollutant X which is being given out through this particular chimney at Roorkee. Okay? So, how do I do that? Or I have an urban airshed here, right? We are assuming that this is the control volume, the whole atmosphere right above the city is the urban airshed. I want to know what is the concentration of compound Y throughout the year, let us say. How is it changing? Let us say if there are different reactions or if the pollutant is settling down or such, how is it changing? Or I have a river here, right, or a canal, let us say, and I am letting out a pollutant out here, and the pollutant is joining the stream out here. So, let us say 10 kilometers down the line or along the river, what is the concentration going to be? Assuming that I know the velocity of flow of the river, the reactions that might be affecting this compound or such. And then here we have the example of lake. So, here if there is an inlet and outlet, or even without an inlet or outlet, but if with just seasonal rainfall and some reactions affecting my compound X, what is the concentration of X with time? How is it going to look like? I want to understand these aspects. We are going to use these aspects, or one comes across these questions quite often in the field of environmental engineering. Closer home to this course, that is water and wastewater treatment, what are some of the similar scenarios that one can come across? As we looked at earlier, we saw the video of a wastewater treatment plant. In that video, we had what we looked at was a sequential batch reactor. We will look at that later, let us say, or we look at the details later. We have this particular reactor, fine, and we had water coming in, and then it is filled to the brim, not the brim, let us say, to a particular threshold, and then we turn off the inlet flow or influent, and then aeration occurs, where during which microbes degrade your substrate or the organic compound, let us say, right. So, I want to know what is the volume of this tank that's required. What is the required volume? We need to design the volume, right. If not, you do not know the capital cost that are going to be incurred, yes. So, you need to design the volume, or you also need to, let us say, design how much the concentration of microorganisms or how many microorganisms need to be present in this particular tank of volume V, such that after certain time, let us say 2 hours, the concentration or the BOD decreases to a particular value. How do I do that, right? So, these are the questions that come up when we are designing different unit process in water and wastewater treatment. So, how do I go about that? So, the key here is understanding that mass is conservative right? It can't be destroyed. At the best, it transforms into another form. So, let us say if I have a continuous flow system, okay, water is continuously coming in, water is continuously going out, and let us assume that this is always mixed or stirred, this is always mixed or stirred, and I am concerned about the concentration of a compound X, given that the rate of formation of the compound can be calculated using the rate constant Kf, and we also have K backward, and assuming that X plus Y goes to Z and A plus B goes to X, rather than forward, okay, formation and loss. Let us say, for example, here this is K loss, rate constant for this reaction via which X is being lost is KL, and rate constant via this reaction where X is produced, we are saying is Kf, rate constant of the formation reaction. So, assuming that I know this information, I can calculate different unknowns or such. For example, at steady state, given a flow coming in and initial concentration of the compound X, what is the concentration of the compound in the effluent, let us say. How do I calculate it? So, we can calculate this by applying what we call mass balance, and I would suggest that people pay attention to this aspect, because you are going to use this considerably or quite often during this class, mass balance. So, how does this help me now, or where does this come from? How does this help me? We just looked at it, we looked at the different applications out here and in the previous slide. But what is the principle here? Principle is that mass that comes in either has to go out or has to be transformed, right? Mass is conserved. If there are reactions occurring, not conserved, but then the transformations also will have to be looked at. So, we are going to look at the principle of, or consider the approach of mass balance. So, for that, what do we need to do? Before I go further to that slide, note that in this class we are going to use one approach for fundamental or for mass balance, and we will look at that equation. But before I do that, I would like to acquaint you with the fundamental mass balance equation. Let me see if I can get that right out here. dC by dt, what is C? C is the concentration of the compound of interest plus the del product of the flux is going to be equal to plus or minus sources and sinks. So, here we have it, accumulation term, concentration change per time. This is the del product, meaning I am trying to get dou by dou x, dou by dou y and dou by dou z. Let us see, when I am talking about del product, this is what I am trying to get it. And flux units are mass per area per time. For example, right now the door to this room is closed. If I open up this door and I open up another door out here and say that a particular compound is coming through that particular door. So, I am interested in the flux, let us say, flux meaning mass coming in through that unit area of the door per time, let us say. So, that is what do we say, flux is about. And in the context of flux, there are two types of transport of mass. So, what are they? One is due to advection and the other one is due to diffusion and dispersion. Okay, let us just try to understand what they are right now. In this room, the doors are closed, no noise, right? That is why we close the doors, no fans are turned on. So, the atmosphere is relatively stable or pretty stable rather, and we have no net fluid flow in any direction, we do not have the fans turned on. So, if I open up a scent bottle here, right, this is an example I use quite often in every class. If I open up a scent bottle here, a bottle of scent here, right. When we say bottle of scent, it typically means a volatile compound. A volatile compound typically wants to stay in the gaseous phase rather than in the aqueous phase or the solvent phase, let us say, right. So, this compound in the scent does not want to stay in this fluid phase, it wants to stay in the gaseous phase. So, right now once I open it, I can smell it only out here. If I leave the bottle out here and go and sit at the end of this, let us say 15-meter room, I am not going to be able to sense it right now, pardon me. But let us say after 10 minutes or 1 hour or let us say 10 hours, I can sense it at the end of the room, or I will be able to or should be able to sense it at the end of the room. Why is that? Due to the concentration gradient, as in here right now the concentration of this compound in the gaseous phase is higher right here, and there it is 0. So, over time again to achieve similar chemical potential, they are due to diffusion, you are going to have transport of the molecules from here to the end of the class, right. So, that we are going to describe by, or we describe by diffusion, Fick's law. Again, we are not going to go into detail in that aspect, but that is one aspect that you need to keep in mind. Another example is, let us say if I turn on the fans, then I will be able to sense the smell at the end of that room, or this room, pardon me, sooner. Why is that? Now I have turbulent conditions in this particular room. So, the dispersion or turbulent diffusion is going to lead to faster transport of the compound within this particular room. So, again diffusion and dispersion, we are not going to look at that in this class though. Advection, what is that about? Again a better example is out here. So, here we have obviously the river or the canal flowing in this direction, and we have some particular plant out here, right, some plant. Is it a sewage treatment plant or something else? I am unable to fathom out here. So, we see that through a particular pipe or such, they are releasing the waste out here, right, and then we see that the compound or the waste is being transported in this direction along the net fluid flow of the liquid or the river, right. So, when we have a net fluid flow in one direction and the compound is being transported along with that fluid, so that is what we call as advection, flow due to advection, let us say. So, that is the example that you see out here. In the next example that we are going to look at, I am not sure if it is remarkably clear, but as you can see, through an underground diffuser or the diffuser at the bottom of the lake, in the middle of the, not lake, pardon me, the canal, you see that the waste is being given out here. But unlike the previous slide that we looked at, we see that with time this width of this waste is increasing, right. So, here it is let us say x, here it is maybe 2x and so on and so forth. So, we know that due to advection, the flow is being, the compound is being transported along this direction, right, that is due to advection, let us say. But why is it being transported along this, let us say if this is x direction, let us say this is y direction, right. Why is it being transported along y direction now? Why is it? Well, that is due to dispersion or turbulent diffusion that we talked about earlier, let us say, but we are not going to consider that, right. Again advection and diffusion. So, here advection is carrying it along with the fluid flow, and obviously diffusion or dispersion, turbulent diffusion or dispersion is leading to this mixing, right, this mixing in this direction, let us see. So, that is something to keep in mind. As I mentioned though, in this class we are not going to look at diffusion and dispersion, we will only be looking at advection. So, we will look at what advection is. Advection, again u dot c dot product, assuming that this velocity, what is this u? U is the velocity of the fluid flow and c is the concentration of the compound now, right. So, the units are mass per area time per time. Assuming that the flow is only in one direction, let us say only in x direction, and then this del product of the flux will turn out to be, and assuming that the velocity is constant, right, u dc by dx, right. What did we assume? Velocity is constant, flow is only in x direction. So, this turns out to be u dc by dx. But if there was diffusion too, let us say, that would have been let us say minus, and diffusion let us say in one dimension, let us say this is the diffusion coefficient dc by dx, let us say. And if I take the del product again in the x direction, this is going to be the second derivative with respect to x, but as I mentioned, we are going to do away with diffusion and dispersion in this class. So, in this class we are just going to look at transport due to advection, right. Advection as in when there is a net fluid flow in one direction and the compound is being transported along with that fluid, that I am referring to as advection, let us say. So, this is what I have. So, what does this equation transform into? Let me write that out here, dC by dt plus, this is what I have out here, u dC by dx, right. U is velocity of flow of that fluid, C is the concentration of that compound, that is equal to plus or minus sources or sinks. As in, if my particular control volume of interest is a lake, let us say, right. We looked at this example earlier. Let us say my lake is this, right. So, mass is coming in and mass is also going out, okay. And let us say there are any reactions occurring within this particular control volume, which is my lake. So, I will have to take care of that in sources or sinks. So, this is the fundamental mass balance equation, and if there are reactions occurring and nothing else, what will that turn out to be? Equal to rate of formation of the compound minus rate of loss of the compound, right. So, dC by dt plus u dC by dx is equal to rate of formation minus rate of loss of that particular compound. But this is the fundamental mass balance equation. There is another equation which is typically applicable for macroscopic systems, which we will discuss later, but this is something that I wanted to mention. As in, if this is the room and this room is my control volume and I open up the door on that end and this end, and we have air flowing in, and while flowing in, if it is bringing a compound in, let us say compound X is flowing in. So, what is that? Mass is coming in, and then the mass is also leaving through this door on my right hand side. Mass is coming in through the door on the left hand side, mass is leaving through the door on my right hand side. Mass coming in, mass going out. And let us say I have a reactor here that leads to decrease in concentration of this particular compound X that is being blown through the door. So, that I have to consider in my sources or sinks, let us say, right. And that is when the system is non-conservative, right. That is what we have, mass coming in, mass going out, and mass being transformed within the reactor here. What is the reactor or the control volume? The control volume is my room out here, right. So, that is something to keep in mind, and we will look at this in great detail. So, advection, we already looked at it, advection and diffusion, and we already looked at this example, the plan or the top view, and applications obviously in every aspect or in every field out there, pardon me. For example, this chimney, and this is my control volume, let us say, and wind which is blowing in one direction. So, that is leading to transport of the compound of interest. So, that is due to advection, and due to turbulence you see this lateral dispersion, right. This is due to turbulence, and then you have different sinks, which is if the particles are heavy, the particle is going to be deposited. So, that is a sink out here, that is due to gravity, let us say, again different example out here. So, just to understand if we have just advection, how is it going to look like, and if it is advection, diffusion and so on and so forth, how is it going to look like. So, here we have concentration and distance, right, and let us say if I put in a tracer at one particular point or such, and at time t1 let us say the concentration is out here. So, at time t2 also the same plug will move, right, and the concentration at time t2 or the distance x2, this is a bad figure if I may say so, here I am talking about distance. So, let us say after it has travelled a certain distance x1 which takes time t1. So, this is the profile, and after it has travelled x2 distance taking time t2, it is again the same profile. Let us say if it is only diffusion, as in there is no flow, right, this is the flow, that is why the particular tracer or plug moved from this location x1 to location x2 with the same profile. But if it is due to diffusion, what is going to happen? Initially let us say due to concentration gradient we are going to have something like this, and then slowly but surely like this and such. Well, it should not start from out here, or if let us say if this is the graph and let us say I put something out here at time t0, after t1 due to diffusion it is going to be something like this, after t2 time it is going to be something like this, right, and T3 something like this. As in diffusion will try to see to it that the concentration is uniform throughout your particular system or volume, let us say control volume. And if you have both advection and diffusion, well, we look at this, and we also looked at the example or the picture previously, let us say. But in general, diffusion is pretty slow. So when, let us say, the flow is going in this direction, we do not consider the diffusion or the transport due to diffusion in this direction. That is something to keep in mind. So let us move on. Another example here, this is from, I believe, the US EPA document. So here we have an injection well. This is groundwater here. Keep in mind that we are talking about groundwater here. And what do we have out here? We have the legend area of tracer cloud in which bromide concentrations exceeded 1 milligram per liter. So the plume we are looking at is when the concentration is greater than 1 milligram per liter for bromide, let us say, right. And we have water table contour levels, predicted path of tracer cloud and monitoring wells. We had the monitoring wells out here, and we have the contour levels. Obviously, as you see 13.8, 75 and so the flow should be in this direction, right. That is something that we understand from this figure. And they injected, this bromide, this particular location, injection well. But did it stay, but did the shape, stay the same at different points in after different times or distances? No. As you see initially itself, this is the plume, and after how many days? 237 days, rather than retaining the shape, right, due to advection, this is groundwater, due to groundwater flow, we have this particular shape. So this particular plume transported from here to here, and it took around 200 and I guess 4 days, right, to go from here to here. But why did it elongate? It is due to dispersion or diffusion, let us say. And because groundwater flow is very slow, that is why you have what do we say, or you can see the effects of dispersion or diffusion and or diffusion in the same direction as the groundwater flow. If it was surface water flow, we would not have seen this. And after 461 days too, we see this profile. Again, an example of understanding, or an example that allows us to understand the effects of advection and dispersion, let us see, right. So that is something we see. Let us see it from the other direction. But with respect to z direction, we see that there is not much dispersion out here. Fine. So again, one example out here. So mass balance, let us come back to what we are discussing, or what we have been discussing. Step 1 is to choose the control volume. When we were talking about the example of this room, what is the control volume? The control volume is this room, let us see, right. This particular cuboid or such, right, that is this particular room, that is my control volume. Then select the substance on which you want to apply the mass balance. Let us say wind is blowing in multiple compounds, so you have to be clear about which compound it is that you are applying the mass balance on. That is what we are trying to mention out here. Is it S or SO2 or so on and so forth. And then try to understand what are all the sources and sinks and such, all the imports and exports, sources and sinks. So here I am trying to understand the mass coming in, mass going out, and then sources or sinks, as in is there any reactor or reaction here leading to the mass of that compound increasing or the mass of that compound decreasing by transformation into another compound. So I need to understand these sources or sinks. And imports, is the mass coming in through the door, or is the mass going in outside, I mean through the door or such, let us see, right. We are talking about the room as an example. So what do we have? Accumulation dC by dt is equal to input minus output. Rate of accumulation is equal to rate of input minus rate of output, obviously, right. So obviously we will also have to take into account import, export and sources or sinks within this particular system. We will look at an example later, but let us go through and understand mass balance. So here I have this particular control volume, right. This is my control volume. So if mass input is Qn into Cn, Qn is the rate of flow of my liquid. So the units will be volume per time, let us say, right. So here we are trying to again understand mass balance in the way that we will typically use it in this class. Fundamental mass balance equation, as discussed previously in this class, can certainly be applied, but we will also be looking at it from a different perspective. So, here let us say you have your particular reactor that you are going to use for your wastewater treatment, and the mass is coming in via this flow of water flow of Qn, right, and the units are volume per time, and the concentration of the compound in that particular flow is Ca in, concentration of compound A. So, the units are going to be what now? Concentration units, let us say I will say mass per volume, let us say, or moles per volume, depending on how you want to take it, right, volume per time into mass per volume. So, as you see, the units will turn out to be mass per time here, right, and then looks like we have a reaction out here. So, mass what do we say, due to the reaction, and we have seem to be having a certain loss. Units of the rate of this particular reaction or any reaction are typically mass per volume per time, right. So, that is why we multiply with volume and we get the same units as what we had earlier, that is mass per time, right, and then mass is again leaving my reactor, right, if not it is going to overflow or such at some point, but we are going to have an output. So, mass output again Q out, flow, rate of flow of the fluid going out, and concentration of A in that fluid going out. So, mass out, again the units as you can see will turn out to be mass per time. So, let us see how we can get this up here. So, we have different terms out here. Let us understand what we have. Again, please note that even the fundamental mass balance equation that we had earlier is more or less similar to what we have out here. So, overall rate of change of amount of material in the system. So, I am concerned with the compound in this control volume, and what am I specifically concerned about? Rate of change of amount of material in the system, overall rate. So, that is what I am referring to as accumulation, right. And then what does it obviously depend upon? It depends upon the overall rate of flow of material, flow, import of the material coming into the system in, and overall rate of flow of material going out of the system, right, input and output, input minus output. And then what else? Overall rate of production of the compound in the system by reactions, let us say. So, are any reactions leading to formation of the compound? That is what we have out here, formed, I guess. And if you are looking at formation of the compound, obviously we also have to look at the overall rate of loss of the compound or material in the system by reaction, that is lost. And obviously if there are any other sinks like settling out of the reactor or such, we are going to have to look at that too. So, this is again understanding mass balance. So, we will look at the applications in the next session because I seem to be out of time. But again, what is it that I have? I am trying to look at how it is that the compound, or I am trying to look at the overall rate of change of the compound in my system, that I am calling as accumulation. That will depend upon mass coming into the system, mass going out of the system, mass being formed within the system due to reaction, and mass being lost within the system due to reaction, right. So, that is what we have. If you look at what we had earlier, dC by dt plus u dC by dx is equal to rate of formation minus rate of loss. So, if we take this term out here and look at what we have, this is what we have. Accumulation term is dC by dt, and this is the this will give you an idea about when it goes to the right hand side, input minus output and formed minus lost, right. Again, but we will try to take this to its natural conclusion, but I will do that in the next session. And as usual, thanking you for your patience, I will end today's session.